going on, besties? In this video, we're going to be tackling ATI TEAS 7 mathematics when it comes to perimeter, circumference, area, and volume. Let's get started. Let's start off by exploring the concepts of perimeter, area, and volume as a whole. To quantify a one-dimensional object, we use a one-dimensional measure known as length. For instance, the length of a given line might be precisely 1 centimeter, a standard unit of measure when it comes to length. If we take that same line and we extend it perpendicularly by 1 centimeter, this is going to transform into a two-dimensional shape, specifically a square. Two-dimensional shapes are quantified by a two-dimensional measure referred to as area. Since our initial line of 1 centimeter in length was extended by 1 centimeter to the right, the resulting square covers an area of 1 square centimeter, a typical unit of measure when we are trying to figure out area. Now let's consider extending that two-dimensional shape up from its plane of 1 centimeter. This new action creates a three-dimensional shape known as a cube. To quantify a three-dimensional object such as this, we're going to utilize the three-dimensional measure known as volume. When we talk about volume, we're quantifying the amount of three-dimensional space inside our object in which it fills. So what is the volume of a cube? Given that our volume of cube was formed by extending a square centimeter up into a third-dimensional shape by 1 centimeter, the volume of this cube is defined as 1 cubic centimeter, a standard unit of measure when we are measuring volume. To make it easier, area is measured as square units and volume in cubic units. Square units results from multiplying two one-dimensional units, centimeter times centimeter, often expressed in exponent notation as centimeters squared or centimeters raised to the second power. Conversely, cubic units arise from the product of three one-dimensional units, centimeter times centimeter times centimeter. This is abbreviated in its exponent notation as centimeters cubed or centimeters raised to the third power. Let's break each one of these three concepts down further and apply them based on the guidelines of the TEAS. So let's start by diving into the fundamentals of geometry when it comes to perimeter. It refers to the total distance or length around a shape. Now, you might wonder, what does it mean to measure the distance around a shape? Well, distance or length is the concept that exists in one dimension. It is quantifiable in units such as centimeters, inches, or miles. This means that perimeter is also a one-dimensional measure, quantified with units of length. So when we talk about a shape's perimeter, we're not just saying 10, we're saying 10 centimeters. Or it's not just 25, it's 25 miles. The specificity of units is crucial when we're discussing perimeter. But then, what do you mean by around a shape? What we mean by this is it's the absolute shortest path around a shape. This is the distance that you cover if you were to trace a line around the shape's border or its edge. A helpful way to understand perimeter is to imagine yourself walking along the edge of a shape, such as this pentagon. Visualize yourself beginning at one end of the pentagon and walking all along the edge of the shape until you reach back to your starting point. That complete distance that you cover is equal to the perimeter of the shape. In our example, we know that every side of the pentagon measures 10 meters. Transversing all 5 sides of this shape is going to equal a total distance of 50 meters. Another insightful method to grasp the concept of perimeter is to imagine taking the shape like our pentagon and separating it from its corners. You could unfold that shape into a straight line. That length from the start of your line to the end of your line is your perimeter. Calculating the perimeter of polygons, which are shapes that only have straight edges, is pretty straightforward. You simply sum the lengths of all the sides and the result of the polygon is the perimeter. Let's practice some examples of how this actually works. We're going to start with a right triangle. The triangle sides are 3 centimeters, 4 centimeters, and 5 centimeters. To determine the triangle's perimeter, we need to add the lengths of each individual side. So we calculate 3 plus 4 plus 5 total gives us 12 centimeters, and that is our right triangle's perimeter. In our next example, we have a hexagon, a polygon with 6 equal sides. This hexagon is described as regular, meaning that every single side is the exact same length. This actually simplifies our task because only one side's length is actually given to us, which is 4 centimeters. We can infer that every single side along this hexagon is going to be 4 centimeters long. Instead of adding each side individually as we did in our previous example, we can actually take a shortcut and use multiplication, since all the sides are of equal length. That's because multiplication is really just repeated addition. To find the total perimeter, we would simply multiply the number of sides, that would be 6, by our length of the one side that we know, which is 4 centimeters. 4 times 6 is going to give us 24 centimeters, which is the overall perimeter of our hexagon. Let's do a more complicated example. This time we're looking at a polygon with 6 sides again, but this one isn't regular. That means that the lengths of each side is going to vary. This example is a bit more challenging because the diagram only reveals the lengths of 4 sides, leaving us with 2 sides that are unknown. Encountering incomplete information is very common in mathematics and also on the TEAS. The strategy here is to leverage the information that we do have to deduce the information that we're missing. Here's how we're going to approach this. Pay attention to the 2 vertical sides that we have here on our screen. 4 inches and 6 inches. Now imagine that you could slide these 2 vertical sides across the opposite side, and both of those sides are going to equal the length of that missing side. So as we know, we have 4 and we have 6, so when you add these together, we actually get a total of 10. We can apply this similar logic to our horizontal sides as well by shifting these lengths that we have available to us of 10 inches and 5 inches. So if we slide those down, we have 10 and we have 5. We're going to add those 2 totals together in order to get the horizontal side that we're missing. So our missing side is 15 inches. By utilizing the lengths we knew, we managed to deduce the lengths that were unknown to us. With the knowledge in hand of every side's length, now we can actually calculate our perimeter. So 10, which is our number up here, plus 4, plus 5, plus 6, plus 15, plus 10 gives us a total of 50 inches, which is the perimeter of our irregular polygon. Now let's step it up a notch by talking about how we calculate circumference and area of circles. It's crucial that you familiarize yourself with the formulas for both of these, as they are going to be fundamentally covered when it comes to the TEAS. The formula to calculate circumference of a circle is going to be circumference is equal to pi multiplied by the diameter. In shorthand, we have C is equal to pi times D, where C is our circumference and D is our diameter. So you might be asking yourself, what the heck is a diameter, right? So if we were to take a circle and we were to draw a line through the center of that circle, that line from one end of the circle to the other end of the circle, that measurement is considered our diameter. An easy sentence to remember this equation is cherry pie's delicious, where C in our cherry is equal to our circumference, pi is of course equal to pi, and the D in delicious is equal to diameter. Now how do we calculate a circle's area? So the area, which is the region enclosed within our circle's boundaries, is area equals pi multiplied by radius squared. So what exactly is a radius? So our radius is actually half of our diameter. So as we know, we drew a line down the center of our circle in order to get a diameter. We're just going to take the diameter and divide it by the number 2 in order to get our radius, which is half the diameter. An easy sentence to remember this equation is apple pies are 2, where the A in apple is our area, the pi is of course our pi, the R in our R is our radius, and the 2 is going to be the square of our equation. A crucial point to remember is that r squared does not mean 2 times r. This is frequently misunderstood among TEAS test takers who first learn to calculate area of a circle. When we're examining both formulas closely, their similarities become apparent. Each formula involves multiplying pi by a specific circle measurement to determine either circumference or area. For circumference, the calculation involves pi multiplied by the diameter, while for circle, it's pi multiplied by the radius squared. How do we distinguish between a diameter and a radius? Well, as we know, the diameter is the line that we draw across the center of a circle that divides the circle into 2 equal halves. That line measurement from one end of the circle to the other end of the circle is our diameter. Sometimes the TEAS is going to give you questions that's only going to give you the radius. Well, in order for us to figure out the diameter based on the radius is we're going to take the radius and multiply it by 2, because 2 times the radius is going to give us the full length of our diameter. So when we're talking about area, we're going to do something a little bit different when it comes to our radius. We're going to actually square our radius. And when we talk about squaring, it is not the same thing as 2 times r. When we square, we actually multiply the number by itself. So if our radius was 2, 2 times 2 is going to equal 4. If our radius was 5, 5 times 5 is going to equal 25. So that is the big key differences between diameter and radius when we're trying to figure out circumference and area. Let's take a look at an example of how this will actually be applied on the TEAS. So starting with our first example, we're given the exact same circle, and our circle is given us a radius of 8. So when it comes to considering the circumference of a circle, we're actually going to multiply the radius by 2 like we discussed before. So in this case, 2 times 8 is equal to 16. So we're going to plug that into our equation. Pi is just a fancy way of saying 3.14 when it comes to your TEAS. So you can automatically manipulate the pi to be 3.14. So we're going to multiply that by 16, and that is going to give us our circumference of this circle as being 50.24 meters. Next, we're going to figure out the area of the exact same circle. So again, we know that the radius is 8, but instead of multiplying it by 2 like we did in circumference, this time we're going to square it. So 8 times 8 gives us 64 meters squared. We're going to multiply that by pi, which is 3.14, and that is going to give us our total area of 200.96 meters squared. Now that we have a better understanding of one-dimensional values of perimeter and two-dimensional values of area when it comes to a circle, let's explore other shapes when it comes to polygons and area. So to grasp this concept of area, we imagine that that 1 meter line in length is going to be dragged across perpendicularly to create another 1 meter line. When we do this, we create a two-dimensional shape. In this case, it's a square. So when we talk about area, we're trying to figure out the measurement within this shaded region when it comes to our different polygons. So we're going to start by trying to figure out the measurement for 3 shapes: squares, rectangles, and triangles. To determine the area of a square or a rectangle, we simply multiply the dimensions of its side. Typically, we're only measuring 2 sides, which would be our length times our width. So if we have in our first example, we have a square that has 2 sides of 2 centimeters each. So we're going to multiply length times width. 2 times 2 gives us 4 centimeters squared. So the area of this square is equal to 4 centimeters squared. Just like with our square, we're going to use the same formula when it comes to our rectangle. So in this case, we have a length of 4 centimeters and we have a width of 2 centimeters. So we're just going to multiply length times width. 4 times 2 is going to give us 8 centimeters squared, which is going to give us the overall area when we're trying to consider our squares and our rectangles. Now, how do we figure out the area of a triangle? So we're going to begin with a rectangle once more, and this time we have a dimension of 3 centimeters by 4 centimeters. Using our previously discussed formula, the area of a rectangle is calculated as 3 times 4 is equal to 12 square centimeters. Now let's imagine that we're slicing this rectangle in half diagonally from one corner to the opposite corner. This action creates 2 triangles, each occupying half of the area of our original rectangle. Given that the rectangle's area is 12 square centimeters, the area of each triangle would be half of the overall area that we saw in our rectangle, meaning that each triangle is 6 square centimeters. This revelation leads us to the formula for the area of a triangle being essentially half of the area of a rectangle. So instead of area equals length times width, the formula of triangle modifies to area equals 1/2 of length times width. However, there's a slight adjustment that we need to note. For our triangle's dimensions, we actually refer to them as base times height instead of length times width. Here's the reason. The labels length times width are suitable for a right triangle, as a right triangle forms precisely 1/2 of our rectangle. However, these terms don't fit as well with other triangle types, like we see with acute and obtuse triangles, where it's less clear which side should be labeled what. In the case of these triangles, we adopt a different approach. We select one of the 3 sides as our base. The choice of the base is really up to you, and often the base is predetermined in mathematical problems anyways. And once we select that base, we envision placing that triangle on the ground with its base being horizontal. Now we have to figure out what is going to be our height. We do this by finding our triangle's peak, also known as the apex of our triangle. Once we find that, we're going to highlight that and draw a little line down until we hit the base. That is going to be the height of our triangle. In certain cases, such as with acute triangles, the line is going to fall within our triangle's boundaries. But for obtuse triangles, this height line extends outside of our triangle's perimeter. Regardless of its position, the formula to calculate the area of a triangle is going to remain the same consistently. Area equals 1/2 of our base multiplied by our height. Let's take a look at a couple different examples when it comes to triangles. We're going to start off with our acute triangle. So as we know, our acute triangle formula is going to be 1/2 times our base times our height, because as we know, any triangle is basically 1/2 of a rectangle. So we have our base is equal to 5 meters and our height is equal to 8 meters. We're just going to go ahead and plug and play. We've got 5 times 8 is going to be equal to 40 meters squared, of course, because we're dealing with area. And then we are just going to divide that overall number by 2. So the area of our acute triangle is going to be 20 meters squared. Now let's take a look at our obtuse triangle. So again, using the same formula, we have a base of 4 and we have a height of 7. So we're going to plug those numbers into our equation. 4 times 7 is equal to 28 inches squared. And we're just going to take that number and divide it by 2. So the area of our obtuse triangle is equal to 14 inches squared. Now let's talk about parallelograms and trapezoids, because they are most commonly tested on your TEAS. Starting with a parallelogram, it kind of resembles a rectangle, but it lacks those 4 right angles typically that you would see when it comes to our rectangles. To determine a rectangle's area, we typically use the formula area equals length times width. We apply a similar approach when we're looking at parallelograms. So let's imagine taking a segment of our parallelogram and sliding it across to the other side of our shape, fitting it in like the perfect puzzle piece. So if we take down here one part of our parallelogram, which is shaped like a triangle, and then add our triangle here down to the end of our parallelogram, this rearrangement is going to transform our parallelogram into a rectangle without altering its dimensions. Therefore, we can still utilize the formula area equals base times height to calculate the area of our parallelogram following those same principles that we see with our rectangle. So in this example, we have a base of 5 and a height of 2. We're just going to go ahead and plug those numbers into our equation, and that is going to give us the overall area of our parallelogram is 5 times 2 is equal to 10 feet squared. Now, finishing off this area section with a trapezoid, you might have noticed that the formula for calculating this trapezoid bears a remarkable resemblance when it comes to triangles. The area of a triangle can be expressed as base times height divided by 2. However, for a trapezoid, the formula adapts to include both bases. Base 1 plus base 2 times our height is all divided by 2. Let's explore why that is. A trapezoid can effectively be segmented into 2 triangles by drawing a diagonal line from the bottom of one end to the top of the other end, depicted by the red line that I just drew for you. This division splits the trapezoid into 2 triangles. The bases of these triangles align with the lengths of the trapezoid's top and bottom edges, and their shared height is identical to the trapezoid's vertical height. In order to find the area of a trapezoid, we could calculate the area of each triangle separately and then sum them up together. But to save ourselves from that frustration, this step can be streamlined by simply adding both bases together, base 1 and base 2, multiplying that outcome by its height, and then dividing it by 2. So taking a look at our example that we have here, we know that we have a base of 8, a base of 4, and our height overall is 6. So we're just going to add our two bases together, multiply it by its height, and divide it by 2. So 8 plus 4 multiplied by 6 gives us 72. And then we're just going to divide that by 2 to give us the overall area of our trapezoid as being area is equal to 36 inches squared. So let's take a look at one more example of a complex shape. So here we have a heart, and we're trying to figure out what the overall area of that heart is. So step 1 is we want to identify the shapes and formulas that we're going to use in order to find the area of our heart. So we have a couple different shapes. We have a square, which is this area that's right here. And then we have a circle formula, which are these areas right here. Step 2 is we're going to start with our easier shape. We're going to start with our square and figure out the area for that. So we know that the square area is length times width. So we have a length of 4 and we also have a width of 4. So we're going to multiply 4 times 4 and that's going to give us the overall area of our square as being 16 centimeters squared. So step 3 is we want to calculate the next shape's formula. So as we know, we have 2 semicircles along the edges of our square. So we need to figure out what is going to be the area of our semicircles. And all we do is we take our equation when it comes to area of a circle, and then we divide it by 2 in order to get the overall area of a semicircle. So starting with our equation, we have apple pies are 2, which is A is equal to pi r squared. That's how we're going to figure out the area. So in this particular case, we know we have a diameter of 4, and we know that in order for us to determine the radius is we have to divide that diameter by 2. So we're going to divide by 2, and that is going to give us 2 as our radius. So now we just need to plug it in. So A is equal to pi times 2 squared. We know that 2 squared is equal to 4. 4 times 3.14, which is the equation of a pi, is equal to 12.56. Now we need to divide this number by 2 because we don't have a full circle. We only need half the circle. So as we divide by 2, that is going to give us overall area of our semicircle as being 6.28 centimeters squared. And finally, in step 4, we can add all of our areas together. We have our 2 semicircles, so each one was 6.28. This is semicircle 1, semicircle 2. And then our last shape, number 3, which we know was our square, is equal to 16. If we add 6.28 plus 6.28 plus 16 is going to give us the overall area of our irregular shape as being 28.57 centimeters squared. Now let's talk about volume. As we discussed before, volume quantifies the amount of three-dimensional space an object fills. We create three-dimensional objects by extending a two-dimensional shape up in height from its plane to create a three-dimensional object. Starting with square and rectangle, projecting these shapes into the third dimension yields a three-dimensional figure known as a square prism or cube and a rectangular prism. Similarly, if we extend a triangle into its third dimension, it's going to produce a triangular prism. To determine the volume, you can simply calculate the area of an initial two-dimensional shape and then multiply that by the height in which you projected it. So if you can understand the area when it comes to squares and rectangles, we know that volume is going to be really easy because the only additional thing that we are measuring here is the height. So in this case, we have length times width times height will give us the volume of squares and rectangles. In our example, we have 4 times 3 times 10 is going to give us the overall volume of 120 centimeters cubed. Next, let's calculate the volume of a triangular prism. Just like with the area of the triangle, we multiply half of our base times our height. But again, we've added an additional unit of measure, which is our length in this situation. So if you can remember the area of a triangle, it's going to be really easy for you to remember the area when it comes to a triangular prism, because the only thing that we are adding is that additional unit of measurement, which is our length. So in this case, we have our base, that is 10, and our height, that is 8, length, that is 50. So we are going to multiply 10 by 8 by 50, and we're going to divide that by 2, just like we would do with area. But this time, our volume, using our new equation, is equal to 2,000 inches cubed. Another easy three-dimensional shape to remember the formula for is going to be our cylinder. So again, the base of our cylinder is just a circle. So how do we find the area of a circle? Well, apple pies are 2, right? So area is equal to pi r squared, just like we see here at the beginning of our formula. But because we made this into a three-dimensional shape, we're adding, or I should say multiplying, one additional unit of measurement, and that is our height. So we're going to take the formula that we have for an area of a circle, and we're going to multiply that by its height. So in our example here, we have a radius of 2, so we just plug that into our equation, and we have a height of 10 meters. So 2 squared is equal to 4 meters. 4 times 10 is equal to 40 times pi, which is again 3.14, is going to give us the overall volume of our cylinder as being 125.6 centimeters cubed. So not all volumes are going to extend into a perfect polygon or circle in terms of height. The TEAS is going to test you on 3 additional shapes: cone, rectangular pyramid, and sphere, that are not going to follow all of those same rules. When calculating the volume of a cone and comparing it to a cylinder of identical radius and height, an interesting relationship actually emerges. The cone's volume is precisely 1/3 that of the cylinder. To visualize this, imagine placing a cone inside a cylinder where both the radius and the height are the same. This setup reveals that the cone occupies 1/3 of the cylinder's volume. This phenomenon is why, when determining the volume of a cone, we apply that same formula that we have for a cylinder, but we are going to divide the result by 3. This adjustment to the formula accounts for the cone's proportional volume relative to that of a cylinder. So taking a look at our example, we have volume is equal to pi times r squared times height divided by 3. So we know that our radius is 5 and our height is 12, so we're just going to plug in our numbers. So this is going to give us pi times 5 squared times 12 is divided by 3. 5 squared is equal to 25, and we're going to multiply 25 by 12 times pi, and that is going to give us 300 pi. All we're going to do now is we're going to divide that total number by 3. And that is either going to give us 100 pi or 314 inches cubed. Remember, the TEAS might test you on both of these examples. As with cones, the same concept is also going to apply when it comes to rectangular pyramid shapes. The base of our shape is just a rectangle, and the volume of a rectangle pyramid is precisely 1/3 of a rectangular prism. When we're trying to determine the volume, we apply that same formula for a rectangular prism, and we're going to divide the total outcome by 3. So taking a look at our equation, we have volume is equal to length times width times height divided by 3. We have a length of 8, a width of 7, and a height of 11. So we're just going to plug in our numbers. 8 times 7 is equal to 56, times 11 is equal to 616, and then we're just going to divide that overall outcome by 3, which is going to give us a total volume of 205.33 inches cubed. Now finally, we have the volume of a sphere. It's difficult to explain the volume when it comes to a sphere without getting into a whole bunch of calculus and how this formula is determined. To save ourselves some time and frustration, I use this sentence to remember this equation. For spheres, we find the space inside with 4/3 pi times r cubed applied. So looking at our formula, we have volume is equal to 4/3 times pi times r cubed. Remember, anytime that we're dealing with volume when it comes to circle, we're going to cube the radius. Anytime we're dealing with area when it comes to circles, we're going to square the radius. So again, we know that we have a radius of 10 inches. So we're just going to go ahead and start plugging in. So we have 4/3 times pi times 10 cubed. We know that 10 cubed is 1,000. We are going to times that by 4/3, and that is going to give us either 2 answers depending on how the TEAS lists it. It's either going to be 1,333.3 pi or 4,186.6. And that's it, besties. I hope that this information was helpful in understanding everything you need to know when it comes to TEAS math, perimeter, area, and volume. As always, if you have any questions, make sure that you leave them down below. I love answering your questions. Head over to nursecheungstory.com where there's a ton of additional resources to help you pass and ace those ATI TEAS exams. And as always, I will catch you in the next video. Bye!